All right, so I wonder if it's because it's recording that this is having trouble. Um, all right, so this is a pipe with water flowing through the pipe, and what I want you to see is that the water very close to the edge of the pipe and the water at the center of the pipe are moving at the same speed. And this right now is an example of inviscid flow. That is, flow with no friction. Um, so that's, we would use Bernoulli's principle to describe flow with no friction. But what I want to do now is turn on the friction. And there's a couple of things I want you to see. The first thing I want you to see is that the water at the edge of the pipe now is moving slowly, and the water at the center of the pipe is moving faster. And that's because of the friction between the edge of the pipe and the fluid. And I hope you can see that the water in the center is moving faster than the water at the edge. The other thing I want us to see is that the flow rate is still constant. If we have 10 meters cubed per second going through this part of the pipe, we still have 10 meters cubed per second going through this part of the pipe, and we still have 10 meters per second, meters cubed per second going through this part of the pipe. So see, friction can't slow the water down. It can't slow down as it moves through the pipe, but what it can do is go down in pressure. So what happens when there's friction is that you have high pressure at the front of the pipe. So here, maybe 17 or 117 kilopascals, or 117 approximately. And if we come over to the end of the pipe, we have a lower pressure. Now, a problem that we're dealing with is the pressure changes with depth too. The higher we are in the pipe, the less pressure there is, and the lower we are in the pipe, the more pressure there is. But it also changes as we move left to right, and hopefully we can see that. So that's about 110 right at the very top, and this is also about 110 right at the very top. Doggone it, we're really not seeing how much the pressure is changing moving down the pipe, because the problem is that the pressure is mostly changing due to the depth, and so we can't really see the pressure change due to moving down the pipe. But that's okay. I want you to know that as we move down the pipe, the pressure gets lower and lower and lower because of the friction. So there is an equation that allows us to figure out how that works. It's one that you will have seen in the textbook. And the way we're going to do it is like this. We're going to say, okay, if we have a pipe and we've got fluid flowing through the pipe, first of all, the fluid is going to be flowing slowly near the edges of the pipe and faster as we get towards the center of the pipe. That's one thing. The other thing is that the pressure goes down as we move through the pipe. We got high pressure over here and low pressure over here. And there are a couple of things we need to remember. We need to remember that the flow rate, that is the volume per second, is equal to the velocity. I guess we call this like the average velocity of the fluid times the cross-sectional area of the pipe. The other thing, that's always true, right? That's the flow rate that's volume per second, or volume per time, and that's measured in meters cubed per second. Okay, so here's the thing. This flow can either be what's called laminar, or it can be turbulent. If the water's flowing through the pipe relatively slowly, then we get this nice steady flow where, again, it's going faster at the center of the pipe and slower as we get near the edges of the pipe. But the flow is steady and it's the same always. If the water starts to go too fast, then we get what's called turbulent flow. And turbulent flow is basically chaotic flow where the water is just moving all around. And even if you wait and look at one particular spot in the pipe, at one moment the water might be moving this way, another moment the water might be moving that way, and that's called turbulent flow. So laminar flow is ordered and predictable, and turbulent flow is chaotic. Okay, and laminar flow happens when the water is moving relatively slow, and turbulent flow happens when the water is moving relatively fast. Okay, if the flow is laminar, then we can predict the pressure change. If the flow is chaotic or turbulent, we cannot. And the way we're going to do this is we can predict the pressure change. The change in pressure from one end of the pipe to the other end of the pipe is going to be equal to 8 times eta times the length of the pipe times Q, that is the flow rate, right, meters cubed per second, divided by pi r to the fourth. So there's a couple things in this formula that are new. Eta is called the viscosity of the fluid. And a fluid with low viscosity flows very easily. Think like hot oil or water. And things with low viscosity, things with high viscosity flow very slowly. Think of like honey or cold oil. So the viscosity can depend on the temperature, but it also depends on what the fluid is. So different fluids will have different viscosities. It's a friction, basically. So if viscosity is low, then there's low friction. If viscosity is high, then there's lots of friction in the fluid. L is the length of the pipe. Okay, so L is the distance that we've moved along the pipe. R, of course, is the radius of the pipe. And that's another important thing to look at here, is that if we cut the radius of the pipe in half, the pressure goes way up, right? This is R to the fourth power. So if we cut the pipe in half, that's going to be 2, 4, 8, 16 times the pressure difference from front to back. So there's a huge dependence on the radius of the pipe. Okay, so that's one of our basic formulas for fluid flow with friction. The other formula that we want is a formula for the Reynolds number. The Reynolds number is a unitless number that tells us how likely it is for the flow to be laminar or turbulent. And we calculate Reynolds number using this formula. It's the density of the fluid times the velocity of the fluid times the diameter of the pipe divided by the viscosity of the fluid. And when we put that all in, it becomes a unitless number. And if the Reynolds number is very high, then the flow will be, if the Reynolds number is very high, then the flow will be chaotic. It will be turbulent. But if the Reynolds number is low, it could be laminar. And a rough cutoff is about 2300. If you're above 2300, it's turbulent, and if you're below 2300, it's laminar. But it's not a hard cutoff, right? If it's right at 2300, we're not going to have any idea if it's chaotic or if it's turbulent or laminar. But if it's less than 1,000 or less than 100, then we say, oh, okay, yeah, definitely laminar. And if it's more than 10,000 or more than 100,000, then we can say, oh, yeah, definitely turbulent. If it's right around 2,000, we're not really sure if it's turbulent or laminar or some mixture of the two. But it's sort of a rough idea of whether or not the flow is turbulent or chaotic. All right, so that's the basic idea of viscous flow, and I'll come back and do a problem.